Zeal Education Society, redefining excellence.
Hello students, in a previous lecture of basic electrical engineering, we have learned the dynamically induced EMF. This principle of dynamically induced EMF is used in rotating electrical machines like AC, DC generators and motors. And the magnitude of induced EMF is BLE sin theta and direction is given by Fleming's right hand rule. Now in this video lecture, we are going to learn the statically induced EMF. Static means stationary. That means here the coils are stationary and necessary flux linkage. See, the flux linkage means nothing but the product of number of turns and the flux produced. So N into phi is the flux linkage. So the necessary flux linkage can be obtained by changing the magnitude of the current. Here are two types again: mutually induced EMF, generally used in the transformer, and another is self-induced EMF. Can we say the example is tube coil of fluorescent tube light. Now let us consider the first one, the statically induced EMF. Statically induced EMF, that is the mutually induced EMF. Let us consider the two coils placed around common magnetic field. Now what is this common magnetic field? It is nothing but a common iron bar or a common iron frame. So two coils are placed on a common magnetic field near to each other, close to each other. Say the coil A, the battery, switch and rheostat is connected, and coil B, the sensitive galvanometer is connected. Now when the switch is closed for the coil A, current will start flowing in coil A and it produces its own magnetic field. So the direction of current is shown here, and as per the end rule which we have already learned, looking from the left hand side for the coil A, the current seems to be flowing in anti-clockwise direction, producing the north pole on the left hand side and south pole on the right hand side. So we can show the magnetic field. The magnetic flux originates from the north pole and enters into south pole. So some flux links to the coil B. Some flux links to the coil B. But there is no deflection in the galvanometer. When the current is changed by changing the rheostat, the flux linked with the coil B changes and EMF get induced in coil B. This galvanometer indicates the deflection, or deflection in the galvanometer indicates that EMF is induced in coil B. Now this induced EMF in coil B circulates the current according to the Lenz's law. Now in this case, the direction of current flowing in coil B is opposite to that of the coil A, that is in anti-clockwise direction, producing north pole on the right hand side and south pole on the left hand side. As similar poles are facing to each other, there is a force of repulsion, and any work is done when there is a opposition to the force. So such an EMF induced in one coil by the change of current in the other coil placed nearby it is known as statically but mutually induced EMF. Its magnitude is given by Faraday's law, second law, and direction by Lenz's law. Now its converse is also true. That is, let us connect the battery, switch and rheostat to coil B and galvanometer to coil A. Then the direction of current flowing in coil B is a downward, which produces north pole at the right hand side and south pole at the left hand side. Once again, you can show the direction of magnetic field. Flux always emerges from the north pole and enters into south pole. So some flux links to the coil A, but as the though the flux are strong, but it is not changing, there is no deflection in the galvanometer. But when the magnitude of current flowing through the coil B changes by changing the rheostat position, by changing the current, as the current changes, flux changes. So the flux linked with the coil A changes and there is a deflection in the galvanometer indicates that EMF get induced in coil A. Now this induced EMF in coil A circulate the current according to the Lenz's law. That is, it sets the magnetic field in a such a way that it opposes the very cause producing it. So the cause of production is change in flux or flux linkage. And therefore, in order to oppose, it circulates the current in upward direction, producing the north pole on the left hand side and south pole on the right hand side, so that it opposes the flux linked via the coil B. So in this way, here also, the magnitude of induced EMF in coil A is given by Faraday's second law and direction by the Lenz law. So we can conclude that EMF induced in one coil by the change of current in other coil placed nearby it or on the common magnetic field is known as statically but mutually induced EMF. This phenomena is generally used in the transformer. Transformer is a stationary machine and there is a flux linkage in the primary side coil and secondary side coil. So here we cannot discuss the transformer. So in this way, now I will write the mutually induced EMF. EMF induced in one coil by the change of current in second coil placed nearby it or on common magnetic field is known as statically but mutually induced EMF. Its converse is also true. That is, connect the battery, switch, and rheostat to coil B and sensitive galvanometer to coil A. EMF will get induced in coil A. The magnitude of induced EMF is given by Faraday's second law, and direction of current by Lenz's law. So in this way, here we have finished the statically induced EMF. Now let us consider the second point, self-induced EMF. Okay, so here it is, self-induced EMF. We have considered only the one coil and the battery, switch and rheostat is connected to it. By closing the switch and changing the rheostat position, we can change the current flowing through the coil, and as the current flowing through the coil changes, flux linked with the coil changes, and such an EMF induced in a coil due to change of its own flux linked with it is known as self-induced, statically but self-induced EMF. The magnitude of the self-induced EMF is given by Faraday's second law, and direction is given by Lenz's law. The induced EMF in this coil is given by, say, E equal to minus n d phi by dt. Negative sign indicate that induced EMF in coil opposes to the supply voltage phi, and that's why sometimes it is also known as counter EMF or back EMF. So I will write here the definition. EMF induced in a coil due to change of its own flux linked with it is known as self-induced EMF. The magnitude of EMF, the magnitude of EMF is given by Faraday's second law, and direction of current by Lenz's law. The induced EMF acts in opposite direction to the supply voltage and hence known as, it is also known as counter EMF or back EMF. So students, in this way, in this video lecture, we have finished the statically induced EMF, that is the mutually induced EMF. This principle is utilized in the transformer. So the mutually induced EMF is nothing but EMF induced in one coil by the change of current in the other coil placed on common magnetic field is known as statically but mutually induced EMF. Its magnitude is given by Faraday's second law and direction is given by Lenz's law. Similarly, we have learned the self-induced EMF. It can application in choke coil of the fluorescent tubes. Here, the EMF induced in a coil due to change of its own flux linked with it is known as self-induced EMF. Here also the magnitude of the self-induced EMF is given by Faraday's second law and the direction by Lenz's law. The EMF induced by the self induction acts in opposite direction to that of the supply voltage and hence known as counter EMF or back EMF. We'll stop here. Thank you.